So let's step back again and reconsider exactly what we're describing here, which is how neurons carry messages, information-rich messages. Like, for example, if you touch here, for example, there's going to be a sensory or afferent cell that'll have to shift towards, the resting potential, where it's not sending any active, currents to an action potential, where you're going to have, changes in permeability of the membrane, and ions moving back and forth and working their way down from the hillock here at the beginning of the axon all the way down to the terminals here at the end. So what's got to happen in order to initiate that action potential? Well, we're going to see it's going to be a change in the polarization around the membrane. And polarization is a term that just means difference, right? And the difference that we're talking about when we're talking about neurons is a difference in charge. So within, the cell, right, it's going to be more electrically negative, right? Again, because, we've got lots of potassium ions, and that's positively charged, yes. But you have far fewer sodium ions right around that membrane because the pump, right, is unequally distributing these ions across the membrane from the intracellular to the extracellular side. So the sodium is being pumped out, utilizing ATP and that sodium-potassium pump, that dual directional transporter. And the potassium is being brought in, but remember, it's being brought in sort of unequally, right? 3 sodium out for every 2 potassium in. So what you're ending up with is more positive ions being shifted to the outside, the extracellular space, and fewer positive ions going to be right there on the interior of the membrane because of that unequal distribution, being accomplished by the pump. In addition, remember, there's lots and lots of these negatively charged proteins that are found inside cells, because that's where cells actually make, protein, right? They make them inside the cell. So, and proteins are made of smaller, constituents, smaller units called amino acids. And a majority of those have a net negative charge. So proteins tend to be anions, negatively charged substances, and you're going to find the majority of them the inside of the cell. So here you're going to have, across the membrane, in a neuron at rest, a polarization, right? Charge difference, a potential difference in charge, right? Remember, that's again taken from the idea that you've got a potential, an electrode on the inside and an electrode on the outside of the cell. And there is a difference, a potential difference, a difference between the potentials that actually rests before a neuron actually, carries an action potential, before there's action between those potentials. And so that minus 65, 65 millivolts, 70 millivolts, more negative on the intracellular versus the extracellular side, that level of potential difference is a level of polarization that is maintained at the resting potential. But there can be changes in that level of polarization. And the way you change the polarization, right, is that you have to alter the permeability of the membrane and allow for ions, which are, the particles that carry charges, to move across the membrane. So, for example, in a neuron at rest, at minus 65, let's say millivolts more negative inside versus the out, at that level of polarization, if we were to somehow add, some open channels, to ungate a few, selective channels for sodium, and that's actually what you do when you press down here on this specialized sensory neuron that will allow for the detection of, light touch. You swirl open channels in the membrane, actually, that allow for some sodium to pass. Well, the forces that we described, right? The electrical force, opposites attract. Sodium's positive on the outside. It now has more holes to allow access to the more negative inside. It'll start to flow in due to the electrical force. Remember the concentration gradient force. There's more sodium outside because that pump has been kicking it out. And of course, sodium comes in extracellularly to begin with because you consume it, right? You're going to, basically see the concentration gradient force drive more sodium from the outside to the in, because the force, stated is that things in high concentration move towards areas of lower concentration. And as you move more, positive sodium from the outside into the more negative interior, you're going to reduce the charge difference, right? You're bringing positive ions from the outside into a more negative internal environment. So you're going to go from minus 65 to minus 60 to minus 55, and you're going to be reducing the level of polarization. Well, the fancy term for the reduction in the level of polarization is depolarization. So by pressing here and opening additional channels that allow for sodium to selectively pass through, driven by the electrical and concentration gradient forces from the extracellular space to the intracellular space, we're going to be making it less negative, right? Going from minus 65, let's say, to minus 55, and we are depolarizing, that cell. And what's interesting is that depolarization is going to lead to an action potential. We'll talk about exactly why, soon. But depolarization leads to an action potential, because depolarization, we're going to see, is going to ungate lots of additional channels to sodium, for example, that will allow a lot more action, between the potentials. Now, you can also do the opposite of depolarization. You can actually increase the charge difference across the impermeable phospholipid bilayer, and to do so, you've got to move different charges. And that means you've got to change the permeability to allow for ions to pass either from the outside in or from the inside out. And, one good candidate for increasing, the negativity of the inside versus the outside, hyperpolarizing, making a larger difference in charge, going from minus 65 to say minus 75 or minus 80 in terms of the polarization, across that membrane, is to allow for potassium ions to leave the cell. Now remember, potassium ions are in high concentration on the inside of a cell because the pump has pumped lots of it in. So it's got, it's utilized, ATP, chemical energy, and converted that to the kinetic movement of the potassium from the outside, where it arrives with your banana or your kale to the inside of the membrane. So you got lots and lots of potassium on the inside. If you were to open additional channels in the membrane to allow for potassium to permeate, to get through that membrane, well, the concentration gradient force, which again states things move from high concentration to low concentration, will drive potassium out of the cell. Now remember, potassium is a positively charged ion in the internal portion of the cell at the resting potential, right? There's a certain level of charge polarization there, charge difference, and it's negative inside. It's minus 65. But, I've told you that, there are fancy equations where you can actually determine precisely, where the net flow of ions will actually be. But it turns out that given the high concentration inside, the strength of that concentration gradient force, the polarization at rest, minus 65, the fact that opposite charges attract is not enough to overcome that outward, concentration gradient force. So, in other words, at the resting potential of minus 65, the electrical force is not strong enough to hold that potassium in. So the net flow will be, driven by concentration gradient. That's the stronger force at that particular level of polarization. But if you have potassium, positive ions from the inside, and a neuron at minus 65 inside versus out, leaving through these additional channels that you've opened in the membrane, well, you're going to be increasing the difference in charge. You're going to be taking positive from the inside out. You're going to be making it more negative on the inside versus the out. And you're going to change the polarization by making it larger, going to minus 75, minus 80. That's called hyperpolarization. And hyperpolarization, we're going to see, actually will make it less likely for a neuron to initiate an action potential, for it to get a current sort of flowing and for it to send a message. We'll talk about why soon. Another way you can actually hyperpolarize a neuron is to allow a different ion to go from the outside of the cell, the extracellular side, to the inside of the cell. This is also going to be driven by the concentration gradient force and opposed by the electrical force, because it turns out the ion in question is an ion that comes in dietarily with sodium. Sodium chloride, which is salt. There's lots and lots of chloride maintained outside a neuron's membrane, at rest. There's not a lot of leakage channels for chloride. We didn't identify any of those in a neuron at rest. So the chloride, which arrived extracellularly, is in high concentration outside the cell. And on the inside, very little chloride. So the concentration gradient force definitely wants to drive it in. But chloride, remember, is a negatively charged ion. And the inside of the cell is going to be at minus 65 relative to the outside, in a neuron at the resting potential. So the electrical force will oppose the entry of chloride. However, at that particular level of polarization, at minus 65, which is maintained for the resting potential, the concentration gradient force is also stronger than the electrical force. So if you were to open channels, in the membrane that allow for chloride to pass through selectively, that high concentration of chloride is going to drive some of that chloride inside the cell at rest. And as you bring negatively charged chloride ions from the outside in high concentration inside, well, you're going to make it more negative on the inside versus the out. And your, level of polarization is going to go from minus 65 at rest, let's say, to minus 75 or minus 80. And we're going to see a hyperpolarization, that entry of chloride into the cell, and it's going to make the neuron less likely to send an electron